Alright, this video is going to go over the properties of quadratic functions. Alright, the standard form of a quadratic is f of x equals ax squared plus bx plus c, with a, b, and c being contained in the set of real numbers, and also the number in front of x squared is not 0. Because if that happened, you'd end up with just bx plus c, so you'd end up with just a linear equation. Alright, and if you use the process of completing the square to modify this standard form, you could switch this to what we call vertex form, where f of x is written in the form where f of x is equal to a times x minus h squared plus k, and the center is of the form hk. So you change the sign on the number in the parentheses, but keep the sign of the number on the outside, the k, the constant at the end, you keep that sign the same. And this thing we call the axis of symmetry. It's a vertical line, because quadratics are upward or downward facing parabola, so the axis of symmetry would be vertical, so it would be x equals, and then the x part of the vertex. Alright, if I tell you to graph the function f of x equals 2x squared plus 8x plus 5, and find the vertex and the axis of symmetry. It might be easier to find the vertex and axis of symmetry first. We can do that by completing the square. Alright, so, if you remember from any previous math classes you've taken, you would factor the leading coefficient out in order to do completing the square. So, factor out a 2. Out of the first two terms, it'd be x squared plus 4x. Then you have plus 5 on the end. Now, this number in front of x, which is 4, you divide it by 2, which is 2. And then you have to square it, so that gives you 4. So, what we're doing is, essentially what we're doing is we're creating what we call a perfect square with that quadratic. But if you notice, if we're adding 4, since we're multiplying it by 2, that's really like adding 8. But we want to balance it out, so if we add 8, we also have to subtract 8. That way, if we were to distribute the 2 into there, everything would cancel out, and so we'd get what we started with up here. But anyway, this x squared plus 4x plus 4, that can be factored down to x plus 2 times x plus 2, and then positive 5 minus 8 would be minus 3, so that would be 2 times x plus 2 squared, and then minus 3. So if you notice your center, or our center, let me write that neater. This is the form. Remember, we have to change the sign on the number with the x, the number on the inside, so it would be negative 2. And the number on the outside, the constant, would stay the same, so it would be negative 3 still. And the axis of symmetry, since I'm running out of room, I'm just abbreviating it AOS. That would be x equals negative 2, because it would be the vertical line that passes through where x equals negative 2. And if we were to graph it, it would look something like, this if you want to see the process they use. See, the book starts with the parent quadratic function y equals x squared, that's your a. The first thing they do is they multiply it by 2 to get the 2 in front. That stretches it out. That doesn't stretch it, that kind of compresses it, I guess. Or stretches it by a factor of 2, I mean, yeah. It stretches it by a factor of 2, makes it more narrow, or twice as narrow. Alright, and then after they stretch it by a factor of 2, since they're adding 2 inside the parentheses, you would actually shift to the left 2 units. And if you're subtracting 3 at the end, that means you would then shift down 3. Now, we're going to go over some more properties of quadratics. This is pertaining to whenever we convert it to vertex form. Alright, whenever we convert it to the vertex form, it might be helpful to know that this value h is equal to minus b over 2a. And this b over 2a, this b and this a, come from whenever originally start in standard form. I figure some people might like to have that formula for h. I don't. I'd rather just remember how to derive it so I don't have to remember 400 million different formulas. I can just remember one process, the completing the square, and that will give me everything I need. But again, some people might struggle with completing the square, and it might help them to just have that formula. So, this h, there's also another formula for k. Positive k is equal to 4ac minus b squared over 2a. The vertex hk in vertex form, if you didn't want to switch out of this right here, you could rewrite the vertex could be found by finding the x-coordinate of the vertex by doing minus b over 2a, and then the y-coordinate of the vertex would be 4ac minus b squared over 2a. Again, I hate trying to remember the formulas. I'd rather just remember completing the square. But every person's different. Also, when the number in front of x squared is greater than 0, it opens upward. And whenever it's less than 0, it opens downward. Before we move on, I just thought of an easier way to describe the vertex. After you find the x-coordinate, you could just take that x-coordinate and plug it back into your function if you don't like this big long formula, the 4ac minus b squared over 2a. If you want, you could just take this minus b over 2a and plug it into your formula if you don't like that long formula for k, and if you don't like the completing the square process. Alright, so without graphing, locate the vertex and axis of symmetry of the parabola defined by the quadratic of negative 3x squared plus 6x plus 1. Does it open upward or downward? Alright, remember the formula would be minus b over 2a. So it'd be minus, then it'd be 6 over 2 times negative 3. So it'd be minus, and then 2 times negative 3 is negative 6. 6 over negative 6 is negative 1. So the h part of our vertex is positive 1. And our k would be f of 1 would be negative 3 times 1 squared plus 6 times 1 plus 1 would be negative 3 plus 6 plus 1, which is 4. So the vertex is the point 1, 4. And that tells you the axis of symmetry is x equals the x part of the vertex, which is 1. And since the number in front of x squared is negative, it opens downward. Alright, now we're going to go over how to find the intercepts of a quadratic. The y-intercept is just when you plug in 0 for x, whatever you get out after that, which will usually just be which should be just the constant term, that would be your y-intercept. Now for the x-intercept, that's a little bit more complicated, if you will. It's not really complicated, it's just a little bit more complex than just the y-intercepts. To do that, we need to look at what we call the discriminant. Remember, the discriminant is the part underneath the square root for the quadratic formula, so it would be the b squared minus 4ac. Remember, if the discriminant is greater than 0, you have 2 roots or 2 x-intercepts. If it's equal to 0, you have 1 root. And if it's less than 0, you have, that should say 2 real roots, meaning the roots you get will be real numbers. But if it's less than 0, you would have 2 complex roots. By complex, I mean they would contain imaginary numbers. They would contain the I, if you will. Alright, use the information from our previous example and locations of the intercepts to graph the same quadratic and determine the domain and range. So, if you remember, the vertex is, I believe it was 1, 4. The axis of symmetry, to remind you, we got x equals 1, and it opened downward. Now we need to figure out something about the intercepts. Let's first figure out how many intercepts it has. If we look at the b squared minus 4ac, that'd be 6 squared minus 4 times a times c. So that'd be 36 minus negative 12, which would be 48, which would be greater than 0. That means it has 2 real roots, meaning it crosses the x-axis twice. So now we gotta figure out how to solve this, how to figure out where the roots are located. Now you could use the quadratic formula if you wanted, but I'm going to use completing the square. In case you've forgotten how we do that, that'd be negative. We get the constant on the other side from the x terms. It equals so, for adding 1 on the left hand side, we would subtract 1, so that's how we get that it equals negative 1 on the right hand side. So now if you factor the leading coefficient out, because we need the number in front of x squared to be 1. Now, let's get rid of the negative 3 on the left hand side by dividing. So if we divide everything by negative 3, we would have x squared minus 2x equals 1/3. So now we take the number in front of x, which would be negative 2, and divide it in 2, or cut it in half. Then you square it. That'd be 1, so you add 1 to both sides. So that means that this quadratic on the left-hand side could be factored down to, actually it'd be factored down to x minus 1 times x minus 1. Then the 1/3 plus 1 would be 4/3. And so, this x minus 1 times x minus 1 would be x minus 1 squared equals 4/3. In case you forgot, if you notice, the number we get after you divide the number in front of x by 2, you notice that went in our parentheses. You can always skip to that step when trying to complete the square. But anyway, if we go and solve for the x minus 1 squared by doing the square root of both sides, we have x minus 1 is equal to square root of 4/3. Alright, the square root of 4 is 2. And we have over the square root of 3. And x minus 1 is equal to negative 2 over the square root of 3. So x is equal to 1 plus 2 over the square root of 3, which would be approximately, I think it's approximately 2.15. And then this 1 minus 2 over the square root of 3, which I think is approximately negative 0.15. So if we graph the function, it would look something like this. So if you notice here, it has the roots we discovered, the x-intercepts of 2.15 and negative 0.15, and the vertex we determined, and the x-symmetry. Alright, so let's move on to part B, the domain and range. The domain for any quadratic is just all real numbers, and the range, since it faces downward, the y values never get any greater than that. So it'd be y, set of all y values such that y wouldn't be greater than, it'd be less than, since it's facing downward. Let me rewrite that, because for a reason it wasn't letting me erase. It's equal to the set of all y values such that y is less than or equal to 4. If you notice, it's increasing when x is less than 1. So for part C, it's increasing from negative infinity to 1. And if you notice, it's decreasing from 1 to infinity. Alright, here's an example. Determine the quadratic function whose vertex is 1, negative 5, and whose y-intercept is negative 3. The graph of the parabola is actually, it's shown below in the picture. So, we can start by using the vertex form. Alright, and we know the vertex, it was 1, negative 5, so it'd be a times x minus 1, because since the point was 1, negative 5, we would change the sign on the x-coordinate, so it'd be minus 1, and then minus 5. Now we need to figure out this a. We know, if you look at the graph, that it contains the point 0, negative 3. So you can plug the 0 in for x and the negative 3 in for f of x. So it would be negative 3 is equal to a times 0 minus 1 squared minus 5. And that would give us negative 3 is equal to a times negative 1 squared minus 5. Negative 1 squared is just 1, so it would be 1a, or just a, minus 5 is equal to negative 3. And that tells us that 2 is equal to a. So our f of x is equal to 2 times x minus 1 squared minus 5. And if we want to write that in standard form, that would be 2 times x squared minus 2x plus 1 minus 5, which would give us 2x squared minus 4x plus 2 minus 5, which would be 2x squared minus 4x, and then minus 3. Alright, now this last example is determine whether this quadratic function has a maximum or minimum value. Then determine that maximum minimum value. Alright, you can determine if it's a maximum or minimum by simply looking at the number in front of x squared. The number in front of x squared is 1, which is greater than 0, which means it faces upward. If it's facing upward like this, the vertex would be a minimum value. Alright, you could do the formula for h, negative b over 2a. So it'd be negative, and then it'd be negative b over 2a. You have the opposite of a negative. That 2a, honestly, that should just be 2 times 1, which would be, you have a negative, and then a negative 4, so that would just make it positive, so it would be positive 4 over 2, which is just 2. So the x part of our vertex is 2. Now we can plug that 2 into our function to find the actual minimum value. Alright, 2 squared, instead of x squared, you'd have 2 squared, which is 4. Instead of minus 4x, you'd have minus 4 times 2, which would be minus 8, and then minus 5. So 4 minus 8 is negative 4, minus 5 is negative 9. So our minimum value is negative 9.